and I would like to spend the next 30 minutes talking about data structures for knowledge management and why it's important that now that we have all of these nice AI toolings for inference, that we spend some time on discussing on which knowledge sources there are and which they can interact with. So let's start with the motivation. Like I said, third day. I hope all of you have many ideas in your head now after these talks, but I hope that there's still some space for a few new ideas. And I think one of the most central concepts that we all work with are knowledge sources. And knowledge sources, they come in many varieties. So let's say in your day-to-day life, depending on your role, I'm sure all of you work with one of these or many of these sources. Let's say you are a Scrum Master or a product owner, and then you may work with Jira tickets more often, where you prioritize and you put new requirements. Say you're more of a developer, you probably work in some Git integration, could be GitLabs, GitHub, or we use Gitty. If you develop APIs, you probably use Swagger or something to put documentation there. And all of these knowledge sources, they have different kinds of schemas and they are disconnected. So it's kind of hard to interact with them at the same time. Probably if you've built some kind of application, maybe some of you have built their own React system, you noticed it's kind of hard to understand holistic informations over all of these different systems. And I don't think it's the solution to say we have one system that everybody has to work in, because these different systems, they are quite good at what they try to do. So all of them, they have some use case they cover. And I don't think we should force people to work into one central system, but we should rather try to basically build a data integration pipeline to take the knowledge from these different sources and then bring it into some format that is machine readable, such that our inference systems can interact with all of the information that is present. And to set off, I'm sure we have very different people on different knowledge levels. So we have to talk a bit about related work just to make sure everybody can follow these ideas. And like I said, I think most of you are probably familiar with vector stores, and maybe you have built your own system. And I think vector stores, they are quite nice because it's especially now very simple to set up, right? You can use Qtrend or Milviews or some kind of vector store. It's also quite cheap to calculate embeddings, and it's quite fast to do vector similarity search, especially with advantages in ANN search. It's very quick to find similar vectors or similar documents. But the main limitations that you face in an industry setting are that you're missing these global connections. So it's quite hard using a vector score to answer a query like, give me all products, for example. Then the vector store, it will return documents, and it maybe return many documents, but it's quite hard to understand, did I get all of something? Because it's not really what the vector store is trying to do, right? You just get some, but you don't really know, have you found all? And you also have a problem with conflicting entries. So let's say, again, you do a query, you get 5 documents, and 2 of them, they say one thing, one of the documents says something else, and the other 2, they are not really relevant. You don't know in a global setting, how many other documents support whatever the 2 said and how many support whatever the 1 said. So which is actually the truth, or which is more reliable information here. And there are libraries like GraphRag. I think that's the most known knowledge graph library. It was developed by Microsoft. If you haven't heard of GraphRag, I really recommend. It's a really nice blog entry just to read it. And it's, I would say, kind of easy to set up because they made it easy to set up, but it's just a library. And they do really powerful community aggregation. So the idea is you have clusters of nodes, and then you do aggregations before. And that's quite nice because then you have this holistic view of your knowledge sources. But the main downside here is that it's quite slow to build and it's only static. So Microsoft, there were issues where people requested dynamic features, and due to these community aggregations, they basically said, we will not do that, that's too much complexity. And also due to aggregations, we lose the traceability to a source document. So at some point, we don't even know where that information comes from, so we cannot provide some citation link to a user, for example. And yeah, it's also quite expensive. It takes a long time, which isn't bad if you do it from a static version, but if you have sources that change all the time, you probably want something that's a bit faster. And since we will talk about graphs, I will just make sure you know which kind of graph we talk about. I think there are 2 big kinds of graphs. We have an RDF, that's a resource description framework. It's basically triplets of entities. And we have a property graph. The property graph is something that was popularized by Neo4j. I would assume some of you have used Neo4j for some graph stuff. I guess it's the most popular graph database that there is. And both of these, you can do basically anything with both of them, but we will use the property graph just because it makes it easier to attach complex structures. Like we would like to attach an embedding, for example, to a node, and that's just easier using a property graph. And if you have worked with graphs, maybe now you think, well, isn't that a temporal graph that you're talking about if we want to have dynamic features? And that's a pretty good point. Temporal graphs are a different kind where you basically can go back and forth through time, and you always keep like track of changes. But I would argue we don't need that capability, because I don't see the point to be like, I would like to know how my knowledge graph looked 3 months ago. I just want a current version that is really good and like correct. So we don't support going back and forth. That's why this talk isn't called temporal knowledge graphs, but just dynamic knowledge graphs. But feel free to look into research on temporal knowledge graphs if you have a use case where you actually need to go back in time to check something out. I think for most knowledge, like search tasks, it's not necessary to go back in time. All right, and then credit where credit is due. This project started as a cooperation with the TU Berlin. I supervised a group of 5 students there for 1 semester, and they basically laid the foundations for this project. It was in a lecture by Professor Tim Teubner. And then the last like 6 months, I spent every now and then, whenever there's time for these nice side projects, to basically polish it a bit, to get it ready to then now present it to you. All right. Next chapter also really doesn't sound interesting. If you have been here to talk before, it was way more visual and way more, let's make it interesting. But I think to talk about formal definitions, it's really important, especially since we now have these powerful AI systems that can create fuzzy schemas that you can basically say, please, please, please create me a nice knowledge graph, and they will give you something. But I think to have a system that you can trust, it's very important to make some formal definitions and to build some kind of structure that you actually own and that you know how to maintain. So we will talk about 4 different types of nodes, which basically make up this graph, and how these nodes are connected, so which kind of edges and nodes we expect there to be. First will be the document node. That's basically a source document. That could be all kinds of stuff. Let's say, for example, it's an HTML page of your internal wiki. And for every document node, we save a content hash. So you can think of an MD5 hash, or we use a char 256 hash, just to have a more like machine-readable thing to interact with the documents. And of course, you could like hit the same hash. I would say will not happen. So we are totally fine with just using the hashes as an identifier. And we save some metadata, so like creation date and last verification date, and that helps to clean your graph, because for us, we want to remove documents that are too old, like a document that was created 5 years ago. Even if it still exists in these knowledge sources, it's probably outdated. It just wasn't deleted by a user. And we generate summaries. That's also done through LLMs, and we store embeddings for the summary just to be able to have more search capabilities on a semantic level. And you can think of this document node as an anchor for all kinds of information that lives in the graph. So basically we build a scaffolding, and document nodes, they only have outgoing edges, which have the type supported by. So these documents, they basically span all of the rest of the nodes, such that we can always trace back information to a document node. And then from the document node, we know where the information originated from and can provide a citation. And in the further illustration, it will just be the small node with the D in it. That would be a document node. Then we have the entity nodes. And entity nodes, this is the actual content that we extracted from our documents. And here we extract a name and a label, and the unique identifier then is name and label. And we will talk about it in detail. We do similarity matching to deduplicate the entities when we insert them, because our goal would be to have a graph that's really connected to then enable something like neighborhood exploration and to really understand how the different documents talk about the same kind of entity, but maybe in different ways. So we need to make sure that semantically like the semantically same kind of entities, they also get mapped to the same node. Because let's say when we have abbreviations or name shortings, then that should be the same node, not two nodes. They all have a path to a document node, could be direct or indirect, and we see relationships between entity nodes. And we will talk about facts. So every node is dependent on facts. Facts will be the next slide. And again, we store embeddings for the summary to enable more search features. And entity nodes are in this blue. The label is dynamic, right? The label is generated when we process the document. So there's no fixed label, but we will, in the illustration, it will be the E nodes. That's some kind of entity. And then there's facts. So facts are basically this atomic nuggets of information. So let's say I have a page in our wiki where I introduce myself, and there's like Jakob works in the data science team, and then some more stuff like where I went to university to and how long I've been in the company. And then one nugget would be that I work with the data science team. And we want to split these nuggets of information to then again merge the same facts and to be able to remove only certain facts. Because let's say we have a fact that is only supported by one document, and then the document gets removed, we only remove that fact. But maybe the node can stay because there's more facts for the nodes which have been supported by different documents. And again, we do similarity matching and duplication just to ensure we have a connected graph at the end. Facts, again, are extracted by LLM. We will see a detail prompt example later. And fact nodes are in yellow and have this F. And then lastly, relationships. Relationships are also nodes. I guess if you work with graph, you would expect a relationship to be an edge. But since we want to have, again, traceability to a source document, we basically take this one edge with the relationship and we just insert a node in the middle such that a document can reference this relationship. But it's just a choice of how we model that. It's basically an edge, but we cannot like point an edge to an edge. That's why we insert a node in the middle. And then an edge is very similar to a fact, or again, like as small as possible, extracted by an LLM, just carries content, and will be this darker blue color. So if we take a step back, that's basically the graph schema. Document nodes, only outgoing edges, which can be connect to very many facts, entities, and relationships. And we see that entities and relationship, this is one-to-one. So every relationship is like between two entities, and then facts are connected to entities. And now I invite you, I will stop talking for like 15 seconds, take 3 deep breaths, think about what I said, and then we continue just to make it a bit more approachable. Okay, let's continue. So now we talk about insertion, deletion, and query. So basically the operations that we enable towards the graph such that we can interact with it. And for insertion, we touched on these points during the last few minutes when we talked about the node structures. But basically we have one prompt that goes over the documents, and then we do a structured output. These are pydantic classes. I think pretty much all of the state-of-the-art models, they support structured output. And we have the structure, we say produce names, produce labels, summary, and then a list of facts. And the source document gets passed into this prompt, and then we just do it again, which works surprisingly well. Like if you just say extract it, and then we prompt like, are you sure, aren't there more? And then sometimes it produces more nodes, sometimes it doesn't. And if it produces the same node, but just with more facts, we do a union, which is just a strategy you can try and see if it works on your cases. Worked quite well for us. And after we extracted the nodes, we then provide to a separate code. We say, this is the nodes that have been extracted for the document. Now extract the relationships. And again, we try it twice to see if we find some more relationships. And then we go into this merging phase. So after we extracted the nodes and relationships, we need to merge them with existing ones before inserting to the graph. And for node merging, we do basically 3 steps after each other, which are more complex after one another. So we try to find matches with a non-complex version and then go to more complex versions. And the easiest would be just an exact match, right? Let's say there's an existing node that's Darmstadt of type place, and we extracted a new node that's Darmstadt of type place. Great, it's very efficient to find. We can just use it and merge these two nodes. And for merging, it would be, that's a cipher. If you're familiar with graph, you know ciphers. If not, just think of SQL, but for graphs, and fill in the gaps. And we return this ID, and then we use the internal ID to merge these nodes. And the cipher basically just match a node with the same label and the same name. All right, if that doesn't work, we use Jaro-Winkler matching. Similar to like Levenstein matching or Jacquard, Jaro-Winkler is just very good for names because it has, values the prefix more than the whole string. So for example, if we have something like Darmstadt, the place, and then we have Darmstadt, the Wissenschaftsstadt. Maybe if you came here by train, it's I think also under the train station, just means science city. You can use Jaro-Winkler, and Jaro-Winkler will give you, I think, 86% for this, so quite a good match because it's actually the same. And then we use an LLM for verification. And if we look at that in the query, again, we use basically the same kind of idea. We search for Jaro-Winkler, and we look if this threshold is greater than our given threshold. And now you see this FalkyDB. So this is the point where I have to tell you which graph database we actually use. We don't use Neo4j, but we use FalkyDB just because we wanted to experiment with FalkyDB. If you use Neo4j, you basically can do the same, just the syntax, this flex.text.Jaro-Winkler would be different then, but Neo4j also has functions for string similarities. And lastly, if all of that doesn't work, we try to match the embeddings, because we have on the descriptions, we have embeddings for them, so we can try to find a matching node based on the description. So let's say in one document, again, a system one, we have Visual West as of type company, and then newly extracted, it's a VV, which is basically an abbreviation that we use quite commonly, and it's organization. So we have a mismatch, but maybe the descriptions are quite similar. Both of them like talk about a fintech, and maybe both of them talk about like, this is our company. So it's quite likely that with a semantic embedding, we can then find a match and actually still merge these nodes. And again, for Falco, these embeddings are stored directly in the node, so it's quite nice. We don't need a parallel structure for searching for embeddings. We can find them, and again, look if the threshold is greater than something, and then in the end, we merge the nodes if the LLM verification worked. And for fact and relationship merging, they work pretty similar. We do all of them at the same time. And our main priority here is to not change information that's already in the graph. Because let's say we have a description that is already in the graph, and then we change that description. It's kind of impossible to then say, well, is that then correct for the documents that already link to it? So we only try to match new ones to existing ones. And then if the new ones can't be matched to existing ones, we insert new facts or new relationships. So basically the priority there is to keep the traceability intact, and secondly would be to maximize the connectiveness of the graph. And the idea is just look at the existing facts, look at the new facts, and then we do some validation afterwards to see that the number of facts didn't change, that the existing facts are actually existing, and basically that the structured output is correct. For deletion, we will go over a quick example, because deletion is now pretty simple when we have that structure and quite fast. So let's assume we want to delete the document like on the bottom left. What we would do, we first just delete the document, like detach delete with also the edges directly to the document. And then next up, we would delete all facts and all facts that don't have an incoming edge from a document anymore. So if you see here, the document also produced an edge to the fact on the right. But when we delete it, the right node down there, that still has an incoming edge. So when we delete facts, we only delete the facts with which don't have incoming edges anymore. And then we remove all entities that don't have a path to a document anymore. And then we remove the relationships that don't form a full relationship anymore. And that's basically it. Now we have deleted the document, and everything that was only supported by this document is now not in the graph anymore. And again, here's the cipher. It's just one query which detach deletes one after another to make sure the graph is then cleaned. All right, then we're already at Inference. And Inference is a work in progress. So be creative here, and these are just ideas because we are still in the process of like using this tooling actually and getting our first experiments. But what we started with is a Pydantic AI agent. You could use LangGraph here, you could use small agent, like any kind of agentic system, you could write your own. And we just provided some tools. So basically, we gave the agent the possibility to query for an embedding. It can query for keywords. So that's like just find a starting node, basically, and then we have this get neighborhood. So the agent, once it has like a starting point, can provide the ID, and then the tool returns the neighborhood of the node. And that's like how the agent can explore the graph and gather information to answer user query. And just to point you to some resources, the nice thing about this dynamic knowledge graph is that for inference, we can just use the same kind of tooling like for normal knowledge graph. Doesn't matter for inference if it's dynamic or static. So there's a project and also a paper called Reasoning on Graphs. There's the GitHub link down here, and like the illustration I put over there. It's great if you just want to get some ideas of how you can interact with the graph. That's also a nice read. And yeah, to provide this tool that enables us to also get some more structure in, we also enable the agent to just write a cipher itself. So it has all the freedom, but it could also use the tools to, then we have a bit more control what the agent is doing. Let's talk about limitations and our outlook before we end. So current limitations are that the graph databases, they are in-memory databases. That's kind of a limitation that you could just solve with using a bigger virtual machine. But if you have really, really big knowledge sources, or if you, for example, also want to save artifacts into your graph database or on the same machine, then you might eventually run out of possibilities here, and their vector stores, something like pgvector, doesn't have these limitations. And the insertion times are quite high. So since we take a few steps here, you need to make a few calls, and merging, especially for large documents and a large graph, can get quite slow. So it's about 45 seconds to insert a document, not too bad, but also if you have like a high throughput, you probably want something that's faster than 45 seconds. And of course, we also, on the development side, we need to put more time into development. It's more complicated to develop such a tool than the vector store. So you should know that if you think, no, I will build that also, it's more effort. And then the last point, I think that's a general problem. We have a few examples where we have like a gold standard, but it's like 50 examples. So we don't have an extensive benchmark set where we can actually say we have a new version, and then maybe 2 documents, they produce a better result and 1 produces a worse result. So it's quite hard to actually get a quantitative feeling of how good your system is. And for Outlook, something that we are working on, maybe you've been at the talk with the Still Labs. We've worked with them in the past as well for small language model training or fine-tuning. And that's a great case because the output is really structured. So we would like to use a small language model here for the node extraction and the relationship extraction, which also provides privacy benefits, right? If that can run on-prem, then you don't have to expose your knowledge sources to some cloud provider. We also want to avoid more recomputation. Usually in knowledge sources, only a small bit of the document changes, like in a paragraph, maybe a sentence added, but most of the document stays the same. So you could apply like aggressive paragraph-based caching to then only compute small parts of the document. And we do not have like live A/B testing currently deployed, but that would also be very nice to give the employers 2 options, basically say these are 2 responses that have been produced by different versions of the tooling. Pick which one you like better, and that could be very nice for us to get an idea of, yeah, the actual usefulness. That's again a quick overview. I will skip over it due to time. And lastly, the dynamic social graph. I guess that's the standard slide at the end. Feel free to connect with me, or if you're interested, you can also check out our job listings. And that's it. Thank you very much. And I'm open for questions now.
Yes, so thank you. We got already some questions. So the first one would be, why aren't fact nodes presented as entity nodes with relationships between them?
fact nodes as entity nodes with relationships between them.
That's
I don't know if I
question.
get the question. So I will try to give the idea about fact nodes. Basically, the fact nodes, the idea is that you always have only linked the fact to an entity, that one fact doesn't link to two entities, to again enable flexible deletions. Because let's say I have a colleague, right, and in his explanation text, he also writes he works with the data science team. If then works with the data science team is a fact and it points to me and the colleague, and then two documents point to this fact node, and one gets deleted, which is my article, and because I switched teams or something, then still the fact node would point to two entity nodes, right? And we wouldn't know like which relationship or which edge to delete. And I hope that answers the question. If not, feel free to talk to me afterwards.
How would you approach treat structured data? For example, a row in a database table as a document with no summary?
So if you have, like in general, I've talked about all of these different knowledge sources. And as a first step, we treat these knowledge sources differently. So basically in the first step where we do the extraction, we have different kind of prompts for different knowledge sources. And this is manual effort, right? You need to understand your knowledge source and the way your knowledge source is structured. And then I would imagine for like relational data, you maybe put your database schema in there and say like, this is the database schema. And then for a row, you could probably still produce some kind of natural language explanation of what this row represents. So yeah, I think relational data should be probably nicer to work with, I would expect. Yeah.
Are you familiar with dynamic ontology technology implemented by Palantir? It looks like you're trying to build something similar.
Like dynamic what?
Dynamic ontology technology.
I don't really know what that is, to be honest. We don't want to be Palantir, I promise.
So
I'm sorry, I don't really know.
Talk afterwards and
Yeah.
check if it's the same. Can you extract atomic facts from a document result in a very large number of fact nodes, especially if the facts, sentences, references depend on each other, like in a long chain of thought?
Yeah, that may happen. I guess that's also one of the limitations, right? It's LLM based. We don't have full control of what's happening. So there may be very many facts that are extracted. Since I would argue, since the modern language models, they have quite large context windows, it's not really a problem if you have 1,000 facts. We see that like needle and haystack benchmarks, it's quite good that the attention works even for large inputs. So I would argue if you don't, like if you get to 100,000 facts at some point, you probably run into problems. But I think this approach for like normal data, I wouldn't see which entity has like more than 1,000 facts attached to it, should work quite well.
How do you quality assure the knowledge graph?
Yeah, I think that's basically one of the limitations, right? I think quality assurance, like at the start, it's just also manual checking, like which nodes are created, do we find the matches that we find? But then long term, it's end-to-end testing. So does the build graph produce the outputs that we would like to see? And also time would be a metric that's important for us. Like how long does an agent interacting with the graph take to find the correct answer?
How do you decide or choose a taxonomy for your knowledge graph?
So at first we just didn't. We just were like, I mean, for entity nodes, right? To decide like which kinds of labels the LLM can produce. At first we were like, just produce whatever you want and trusted that the parameterized knowledge will choose somehow the same kind of labels for similar inputs. But we went to provide some, like a set from V3, the ontology standard. Like we provide, I think it's 30 labels, like the most common labels. They're like, try to use these labels. If you really can't, use something else. But that's the fuzzy part, right? That's the fuzzy LLM part where we don't have like strict guarantees that it won't choose something different.
Okay. So one last question. What does the text, oh no, it's just switched. What have been the reasons to not use ontologies like RDF? Was this a topic of complexity?
Well, I guess. So basically, like to provide metadata directly into the nodes, I feel like it's more intuitive that they are inside the node, something like creation date. But also, for example, the vector searches, I'm not familiar with a RDF-based graph database that can directly support something like vector search. And Falco and Neo4j, for example, these are the two most prominent players which also support these features, which are important to us because we want to still have this semantic features, even though we don't work with the vector store directly. They are property graphs, and so it just felt like it makes sense to use a property graph instead of an RDF graph.
Okay, then thank you. So there were more questions, so I guess you can also ask him afterwards. Yeah, thank you for your talk. Thank you for your attendance.